Hello everyone, my name is Changshuo Zhang from Renmin University of China, and today I will represent our work titled Test Time Alignment with Dataspace Model for Tracking User Interest Shifts in Sequential Recommendation. Let's start with the problem we are solving. Sequential recommendation predict the next item a user will interact with using their historical behavior. But real-world user interests are dynamic, and they shift over time. And for example, a user might focus on study-related items on weekends, but on weekdays, but switch to sport gear on weekends. If a model trained on weekday data keeps recommending books on weekends, it fails. And to validate this, we split test data of two datasets, moving length and margin, into 4 time segments. By the time step. As you can see, the later segments and its have a bigger interest shift, shows a worse performance for static model like Rec and Mamba for Rec. And this proves that static model can't adapt to test time user interest shifts. And 2 key challenges emerge here. And first is how to capture temporal dynamics. For example, the time gap between the interactions. And second is how to dynamically track evolving the user interest patterns during the testing. And to address these challenges, we propose the T2RAC, which combines 2 core ideas. The first is test time training. And unlike the static models, T2RAC adapts its parameters during the testing using the unlabeled test data. And the second is dataspace model, and we use the Mamba 2 as our backbone. And why use this? Because it handles long sequences efficiently compared to the transformers. And explicitly models the user interest states and is critical for tracking user interest shifts. And T2 has 2 unique alignment models to enable adaptive testing, the time interval alignment and the interest state alignment. And let's break this down. First is the time interval alignment, and the goal here is to align the model's learned time step with the real-world time steps. And here's how it works. And during the testing, and the model generates the dynamic time gaps, the delta from the user interaction sequences. But the delta only uses the user behavior past time step and ignores the prediction time step, which means the time when the recommendation will happen. And we solve this by reusing the model's output embedding the ON to estimate the missing time step, the delta n+1. And we then compute a ground truth time gap sequence from the real time steps and align the learned delta with a pairwise hinge loss. And this loss preserves the relative order of the time intervals, and not just the absolute values. So the model learns to sense how the time gaps related to the interest shifts. Like knowing a long gap between the interactions might mean a new hobby. And the second, the interest state alignment. And this model ensures the model's interval representation of the user interest is consistent, even as interest shifts, and here is the intuition. The user interest shifts often happen at the end of the interaction sequences. For example, the last few items a user interacts with. So we focus on the final state of the services model, and this state combines of all historical behavior and the latest preferences. And these steps, we first forward the final state, and then we backward the state, and then we use alignment loss to maximize the differences between the original final state and the reconstructed final state. And we even provide a theoretical guarantee that provides upper bound of this loss, ensuring it stabilizes the model during test time updates. And let's walk through the T2RAC test time process. First, it saves the original model parameters that we deploy online, because we don't want to permanently change the pre-trained model. And the second, for a few training steps, we first forward pass like the time steps, the final state, and output, and then we compute the self-supervised losses, like I suppose the time interval loss and the interest state loss, and then we update the model parameters using these 2 self-supervised losses, and this losses is no labeled test data needed, and we make the final next item prediction with the updated model. And finally, we restore the original parameters for the next batch. So each batch's adaptation doesn't affect others. Now let's look at the results with tested T2-Rec on 3 datasets, the movie lines Mamba and Zhihu, against 8 baselines, including static models like SysRec and time-aware models like TSysRec and TeamFrec, and other taxonomy training-based models like taxonomy training for recommendation. And the key takeaways from the table, our model T2-Rec outperforms all baselines across all metrics like recall, MR, and NDCG. And on datasets with larger interest shifts like Mamba and Zhihu, the performance are even bigger. We also checked the key practical concerns that effective on the shifts, as shown in the figure. T2-Rec's advantage grows with larger insert shifts, the segments 3 and the segments 4. This proves it's not just better overall, especially better at handling the problem we set out to solve, the user interest shifts at the test time. To wrap up, our T2-Rec addresses dynamic user interest shifts by combining taxonomy training with two-alignment models. It uses space model for efficient long-sequence modeling and explicit state tracking. And the experiments on 3 datasets shows our model outperforms the baseline, especially when the interest shift happens. And we are excited to explore the online deployment of our model next. And thank you for any questions.
Could you summarize the key advantages and, in case also the drawbacks, with respect to conventional sequential recommended systems?
Okay, the key advantage, I think, is timeliness. Like some modern recommendation systems, and because 1 year ago, maybe our use some daily updated models that doesn't have enough timeliness. Today we use some streaming recommendation that we receive models batch and batch, and we continuously update the parameters, like some short video platforms. But my work compared to these models that we can train the models at the test time. Usually the baselines that train on datasets and the training data have labels, but test time doesn't have labels. So how we build some losses on the test data, and we use the test time data to update our models. It have a bigger timeliness compared to the baselines. I think it is the core advantage.
How are the latencies of your model during inferences? Aren't the latencies higher?
We propose some offline throughput in our paper, but not here. And this work doesn't deploy online, but I have some previous work on the ranking stage that I trained the data at the test time, and it serves well. It truly have a future for the taxonomy training, yes. And we have some experiences for the taxonomy training, yes.